Madam, good evening.
Yes, we are about to start the session. I hope I'm audible and my slides are visible.
Yes, ma'am.
Okay. Good evening. I welcome you all to the ninth tutorial of this course, Reagents in Organic Synthesis, which is conducted by NPTEL, whose course instructor is Professor Subhas Chandra Pan from IIT Guwahati. And I'm Deepika, your PMRF teaching assistant. I'm doing my PhD in organic chemistry at IIT Bombay. So, in this week's video lectures, there were three video lectures this week. In fact, last week, where Sir has talked about few more organometallic reagents which are used in organic synthesis. So, this is basically the replacement of last Friday's tutorial, which got postponed due to unavoidable reasons. Okay. So let us solve a few more questions on the topics covered in the week 9. So these are the first two questions from today's session where you can see these two must be very easy for you by now. Okay. So you see an alpha beta unsaturated ketone here where you have this double bond in the alpha beta position and here you have the keto group. Okay. And this one, if you see, Me2Culi, okay? So, dimethyl copper lithium is there in the reaction medium, and in the second step, you have acetic anhydride, okay? So, this question is from the topic organocuprates, okay? So, what happens as you have already gone through the mechanism in the week 9, lecture 1, you must have already known that organocuprates, when it comes to 1 2 or 1 4 addition in alpha beta unsaturated carbonyl compounds, in those cases the organocuprates would prefer 1 4 addition. Okay, so definitely the methyl group from the dimethyl copper lithium will start add to the fourth position. That means the methyl nucleophile would attack at this position and the arrow pushing will go like this, and the ketone, if you visualize in this way, the enolate you will get in this way. Okay, now if you see, you have acetic anhydride in the second step. Okay, so what will happen, methyl will add here, and whatever oxyanion you are going to get, that oxyanion will now is capable of reacting with the acetic anhydride. Okay, so it can further see, this is the new carbon carbon double bond which will form, and here you have the oxyanion of the enolate, and here you have the OMe, uh, Okay, here you have the OMe, and here you have here you have two methyls. So basically, now this oxyanion is going to react with acetic anhydride in this fashion. The other acetate group you can visualize here. So that arrow you can attack here and the acetate leaving group will be knocked out. So ultimately you will get a product of this type. Two methyls will be now added to the fourth position where you have already one hydrogen also, and here CH double bond. In one side you are having OMe from the substrate itself, and on the other side now you have OAC. Okay, so when you are treating your substrate which is alpha beta unsaturated carbonyl compound and you are not quenching the reaction with moisture or water, rather you are quenching it with acetic anhydride, then the enolate which is going to be generated is going to trap acetate in this fashion. Okay, so this is the product you are going to get. Now coming to the next reaction, in this one also you have an alpha beta unsaturated ketone. Okay, so although this is a very large molecule, as you can see, you only have to focus on this part of the molecule which is containing the alpha beta unsaturated ketone. And here also if you see, we are not quenching the reaction with moisture or water. Okay, here what you have, this uh, two ethoxy groups are attached to phosphorus center, which is again attached to a good leaving group which is chloride. Okay, so in place of the acetic anhydride this time we are using this phosphonyl chloride. Okay, so the first step, as you already know, the methyl nucleophile is going to get added to the fourth position. Okay, in this fashion, and whatever an enolate you are going to generate, that oxyanion is now going to trap this reagent after knocking out the chloride. So I hope you can write the product by yourself this time. Okay, nothing, just a new carbon-carbon double bond will form here and O phosphorus bond will form because of the quenching with this phosphonyl chloride. And if we had used say ammonium chloride solution in water, that time you would have gotten simply alcohol here. Okay, with the addition of methyl at the fourth position. So you have to note down how we are quenching the reaction ultimately. So after this, let us come to the next questions. Again, these questions are also from the same topic, organocuprates. Here again we have this particular compound where we have two double bonds. Okay, out of which one is simply terminal olefinic double bond and the other one is alpha beta unsaturated ketone. So if you have to choose between these two types of double bond, or say you have to choose between ketone and double bond, you have to always go for the alpha beta unsaturated ketone double bond. Okay, this will come from the mechanism which is supported by hard soft acid base concept. Okay, that part if you want to revise, you can go to the first lecture of this week. Okay, sir has explained thoroughly about how hard soft acid base rules are governing this addition in case of the organocuprates. Okay, so in this case also, according to the HSAB principle, the incoming nucleophile is going to prefer the alpha beta unsaturated keto double bond above this terminal double bond. So you are going to simply get the product where you are going to have the addition of methyl at the junction. Okay, see, this is the product you are going to get. And here, when it comes to the quenching part, we are not adding another reagent which can get trapped by the oxyanion of the enolate. So here simply the workup will give you back the, suppose if I write the intermediate product, you will get the enol here. Suppose O minus will form first, and here you will get enol, and then this part will remain same. Just here the addition of the incoming methyl will take place. Okay, so this is going to be the product that you are going to get. Now in the next question, again you have this alpha beta unsaturated ketone. It is not only alpha beta unsaturated from this side, also it is benzylic from this part. Okay, because this phenyl ring is fused with the ring which is containing this keto group. Okay, so you have again two different moieties, and you have to select one of them, that this methyl nucleophile will attack at this position or this position. See, aromatic substituents whenever you have in this way, those are very stable in itself because of the aromaticity and conjugation of the pi electrons. Okay, so if you have another moiety which can undergo reaction without disturbing the aromatic fragment, then always choose that part. Okay, that means if I show in this molecule, you already have a moiety present on this side which can undergo reaction with the dimethyl copper lithium, okay, without disturbing the aromatic side, which is in itself very stable. So that this part only will first undergo reaction with the incoming nucleophile. So likewise, you can see that this incoming nucleophile is getting added to the alpha beta unsaturated double bond, and since we are again not adding any external reagent which can get trapped by the enolate, you will simply end up with the enol first, which will tautomerize to the ketone again. Okay, so this is how you are going to get this particular product without disturbing the aromatic substitution. Next, let us move to the next question. This is from the part organocuprates, which is Lipschutz reagent. Okay, this particular organocuprate reagent is called as Lipschutz reagent. And if you remember from the lecture 1, Lipschutz reagent shows more selectivity and radioselectivity as compared to the dialkyl copper lithium. Okay, so this reagent is, if you compare, is less reactive and more selective. So now in this particular case you have a reactive site in this position. Okay, you do not have any ketone or any alpha beta unsaturated functionality in this time. This time you have this epoxide. Okay, so what happens when you take such reagents which are acting as nucleophiles? In that case, the epoxide ring in the substrate will open up. Okay, now the question is, this epoxide will open up from which side? Say this or this. Okay, these two sides are present. So in such cases you always have to attack at the epoxide ring from less sterically hindered side. Suppose if I number this carbon as 1 and this carbon as 2, if you look at the carbon number 1, it is tetra substituted. Okay, that means it is already highly sterically hindered. Whereas carbon number 2 is only tri substituted, so it is comparatively less sterically bulky to than 1. Okay, so here also the ethyl nucleophile will open up our epoxide from this position, and the epoxide ring will open like this. So you are going to get this particular product as your final product. And if you look at the yield of the product, it is very excellent. Okay, 98% of yield you are getting with the Lipschutz reagent. And this is how, when it comes to these type of nucleophilic addition reaction, Lipschutz reagents are more or less preferred. Okay, so moving to the next question. Again, it is from the topic organocuprates, but this time it is a coupling reaction. Okay, to be precise, it is similar to Karyochotkiewicz reaction. Okay, so we are starting it with aryl halide 1, and at first we are treating it with butyl lithium. So what will happen? First, the butyl lithium will undergo metal halogen exchange with this, and in the first step the species that we are going to generate is the lithiated aryl anion. Okay, so this highly reactive species we are going to generate in the first step. Then comes copper cyanide. So this copper cyanide is going to in situ generate our Lipschutz reagent in the reaction mixture. Okay, this is basically the procedure for generating in situ Lipschutz reagent for these type of coupling reactions. Okay, let us look at the deep mechanism how this reaction is going to happen. See, first this aryl bromide, like I said, will undergo metal halogen exchange in presence of butyl lithium. Then two equivalents of that metal halogen exchanged product is going to get copper cyanide insertion, and the Lipschutz cuprate will be generated in situ. Okay, and this is the proper mechanism which has been presented by the research paper from which I have taken the question. You can see that aryl and copper monomer in this fashion will form first, which will lead to the formation of a metalla cycle, which is basically the dimer of the aryl copper complex. Okay, and that dimer, which is the metalla cycle intermediate, is going to undergo reductive elimination at the end to give you the coupled product. Okay, so this is how the coupled product is going to be generated, and the reductive elimination is going to be helped by the benzoquinone, which is also present in the reaction medium. Okay, tetramethyl 1,4-benzoquinone is also present. So this is how you are going to get the desired product. So, okay, again this is another coupling reaction which is very very interesting. We are starting it with the monoalkyne with the substitution of R. R can be any alkyl group, okay? And we are treating it with copper iodide in presence of ligand L3. This can be any organic ligand you can consider, and K2CO3 base is used, and in presence of DMF solvent. Okay, so mainly copper is playing the role in this reaction. Okay, and if you remember the name of the reaction, this is nothing but Glaser coupling reaction. Okay, where you start with a monoalkyne and you end up with a dialkyne of this type. Okay, which is synthetically very very important fragment. Okay, so let us look at how the reaction mechanism is taking place in this particular reaction. So suppose the reaction is carried out in presence of this L3 ligand, okay, and we are starting with this monoalkyne, okay, and in presence of the K2CO3 base, deprotonation from the alkyne will take place because of the presence of this highly acidic proton on the alkyne. Okay, and after deprotonation, the copper metal insertion will take place to the anion. Okay, because copper iodide is present in the reaction medium, so copper insertion will take place by simply knocking out the iodide leaving group. Okay, so this type of copper alkynyl intermediate complex you will observe in the course of the reaction. So now, as you know, in Glaser coupling, atmospheric oxygen also plays a part. Okay, so in this case also, when this complex is formed, where you can see that monoalkyne is now coordinated to the copper metal, which is already containing two neutral ligands. Okay, two such fragment will now couple to give you a metalla cycle of this type. Okay, two of these complexes will now combine to give you a four-membered metalla cycle, and at the end this will undergo reductive elimination to give you coupling of both the alkyne fragments, and you will get the desired product in this way. Okay, so this is how this particular Glaser coupling reaction is going to take place. I hope this is clear. Next up, we have another example of Glaser coupling, but this one is a little more complex. Okay, and also this is not using any copper, rather it is actually using iron and zinc this time. Okay, so most of the Glaser couplings and Hay couplings, Hay means heteroalkyne coupling. Okay, so Glaser or Hay coupling, most of them are carried out in presence of copper catalysts. Okay, but this particular example, which is an exception, is being carried out in presence of iron and zinc metals. Let us look at the mechanism. The mechanism is more or less similar to what is followed in Glaser coupling. Okay, so let us move to the mechanism step by step. Okay, so this is the substrate from which we are going to start. Okay, see, first we are adding zinc to the reaction medium. So zinc metal insertion will take place to give you a zinc bromide complex of this type. Okay, zinc metal insertion takes place, and in presence of moisture in the reaction medium, this carbon zinc bond will break, and the anion will simply take up a proton from the environment to give you this debrominated alkyne. Okay, so if you go back to the question, you will see this one alkyne first undergoes reaction with zinc, and in presence of water in the system, it will give you this debrominated alkyne. Now let us bring the other fragment of alkyne which is given in the reaction medium. Okay, now both these terminal alkynes are present in the reaction system, and we have a base also. See, potassium hydroxide base is present in the reaction medium. So potassium hydroxide will now take up acidic protons from both the alkynes. Okay, and this is how we are going to get these alkynes generated at the terminal positions. Okay, so till here we could see the function of the zinc metal. Okay, now the iron metal will come into picture. We have FeCl3 in the reaction medium. Okay, so that FeCl3 is going to generate two species of this type. Okay, in one species you can see that both the alkyne fragments which are coordinating to the metal are different, and in the second fragment, due to the more number of equivalents of the first alkyne, you will get homo coordination also. Okay, so both these two alkyne fragments which are coordinating to the metal are same in the second moiety. Okay, now both these two moiety, like we have already seen in the previous Glaser coupling example, will undergo reductive elimination to give you these two hetero and homo coupling products. And the further cycle of the reaction, if you see, are nothing but the regeneration of the catalysts. Okay, at this point you are going to get your desired products, which are hetero and homo coupled product. So this is how this reaction is going to take place in presence of FeCl3 and zinc catalysis and potassium hydroxide base in water medium. Now let us move to the next part. Okay, so this is basically from the topic organochromium reagents. Okay, and this particular example is from Dodds annulation. Okay, so what happens in presence of organochromium reagent, two acyclic, two or three acyclic fragments can undergo annulation reaction, which is known as Dodds annulation. Okay, so in this particular reaction, if you notice that we are starting with these two acyclic molecules, one of which is containing this pentacarbonyl chromium fragment and the other is nothing but a terminal alkyne. Okay, so in the first step what will happen, you can consider a 2+2 cycloaddition reaction between this terminal alkyne and this carbon chromium double bond, and that 2+2 cycloaddition reaction will give you this four membered metalla cycle. Okay, but this four membered metalla cycle is very unstable, so this it will immediately fall off to give you this type of a intermediate product. That means you can visualize it as the breaking of the shift of this bond towards here and this bond towards here, and by opening this metalla cycle, which is four membered, you are going to get a triene of this type, where one of the double bond is carbon chromium double bond containing fragment. Okay, so now you have this triene. In the subsequent step, this carbon which is containing the chromium moiety is going to generate a carbene now. Okay, so if I write that carbene intermediate of this reaction, here you will have N-butyl, and at this position you are going to get the electron deficient carbene. And the rest part will remain the same. Okay, now this carbene will undergo reaction with this terminal double bond to form a Baldwin covalent six-membered ring of this type. Okay, and when this product is treated with acidic environment, in that case what will happen, if you see, first this methoxy will get protonated, here you will have positive charge, and methanol elimination can take place. And in the subsequent step, see here, due to the leaving of methanol, in the subsequent step you are going to get a carbocation, okay, which is then attacked by a water molecule which upon tautomerization can give you the desired ketone. Here you have the cyclopropane, which formed because of the reaction with carbene and the terminal double bond. So this you are going to get, which will subsequently tautomerize to give you the ketone product. Okay, so this is how this Dodge annulated product you are going to get, which is involving this organochromium fragment. So another question from the annulation reaction portion. Here again we have a organochromium fragment in the substrate, which is again coordinated to 5 carbon monoxides, okay, carbonyls. Now in this case what will happen, it will be the similar case like we saw in the previous case. At first this triple bond will undergo reaction with this carbon chromium double bond, okay, and you are going to get this type of intermediate by carbonyl insertion at this position, okay, between this chromium metal and this carbon. We are going to get a carbonyl insertion, and this type of similar carbonyl insertion you can observe in case of Poisson-Khand reaction, okay. If you go through Poisson-Khand reaction as well, you will find a similar carbonyl insertion of this type. So basically you are going to get a 5-membered metalla cycle as the intermediate in the reaction, which will immediately undergo beta hydrogen elimination to give you the second intermediate, where the newly formed carbon-carbon double bond because of beta hydride elimination, like see, this hydride we are eliminating, so you are going to generate a double bond in this place, and that double bond is now going to coordinate to your chromium metal. So a kind of rearrangement will happen this time, which is known as reinsertion, and this time the chromium metal is now going to be inserted between the carbon of the carbon monoxide which got inserted and the carbon which is containing the alkyl substituent here. So a new intermediate metallar cycle you are going to generate. Now reductive elimination will take place, and because of reductive elimination, this copper fragment will completely be knocked out, and this carbon and this carbon, these two carbon atoms will couple to give you this 5-membered alpha beta unsaturated ketone. Okay, this completely substituted pentanone fragment you are going to generate starting from 2 acyclic molecules. Okay, so this Dodge benzannulation or Dodge annulation is considered to be a very important methodology in case of the total synthesis of natural products or biologically active molecules. Okay, so this methodology is very important for the organic chemists who are working on natural product synthesis. Okay, moving to a very easy question from organochromium part. So we have an aldehyde here, RCHO, and R-X, which is an alkyl halide, and in presence of two equivalents of CrX2, where X can be any halide or preferably CrCl2, we can see that the chromium metal insertion takes place to give you an oxygen chromium bond of this type, and since we are using two equivalents of chromium chloride, CrCl3 will be eliminated in the reaction. Okay, and this oxygen chromium bond will be subsequently cleaved by water to give you alcohol. Okay, this is a very easy question. Again, another easy question from the same topic. Here what will happen? We are taking again two equivalents of chromium chloride. Okay, again chromium metal insertion will take place and you will get a organometallic compound of this type, which is containing carbon chromium bond. Okay, and this fragment you can visualize as anion here and CrX2 positive here. Okay, so this anionic part will now going to attack at the aldehyde carbonyl functionality, and you are going to get the enolate, which is now going to have the CrX2 counter cation, and that O chromium bond will be broken by water in the workup stage to give you this alpha beta unsaturated alcohol. Okay, I will just take a 2-minute break, and after 2-minute break we will resume the class. Okay. Okay, thank you so much for waiting. Okay, so I hope this is clear. Now, this is from the topic Nozaki Hiyama Kishi, okay, which is involving again organochromium reagent. Okay, we have already discussed some examples of Nozaki Hiyama Kishi coupling reaction in our previous class. So let us discuss one more example, which is this one, and let us look at how this reaction is going to happen. Okay, so if you recall the mechanism, what happens in Nozaki-Hiyama-Kishi, this reaction involves chromium chloride and nickel chloride, okay, which is nickel metal in +2 oxidation state and chromium metal in +2 oxidation state. So what happens? You can observe that the chromium +2 is going to reduce the nickel +2 into nickel 0 oxidation state. Okay, and this nickel 0 oxidation state is basically going to drive the reaction forward. Okay, so what happens? We have a alkyl halide, or in this particular case you can see this vinyl triflate we have. Okay, so this vinyl triflate is going to undergo oxidative addition to the nickel 0 metal. Okay, and that oxidative addition will result in the change in the oxidation state of nickel from 0 to +2. Okay, and this oxidative addition product is now going to react with the chromium 3, which was initially generated in the reaction, and metal exchange, which is known as transmetallation, will take place, where you can see that chromium 3 is now going to replace our nickel +2, which was present between the alkyl group and the leaving group. Okay, so we are going to get the organochromium complex of this type at this part of the mechanism. Now, the introduction of the carbonyl compound, either aldehyde or ketone, will take place, and this organochromium complex is now going to shift this R1 alkyl group to the carbonyl carbon. Okay, so because of the shift, you are going to generate a new species of this type, where the oxyanion which you are going to get is taking the chromium 3 plus X as the counter cation. Okay, and after this we carry out the workup like we saw in the previous two questions, where the workup step is going to introduce water to our this oxygen chromium bond containing intermediate product to break the oxygen chromium bond, and you will get your desired alcohol R1 or R2, R3 here, and here you will have the hydroxy group. Okay, so if we go back to the question, you can see that this vinyl group is transferred to our aldehyde. So this group is going to be added here, and as at first you are going to get oxygen chromium bond, okay, which will be then hydrolyzed using water. You can see here workup with water is mentioned, and that water workup is going to give you 74% of the desired secondary alcohol. Okay, so this is how the Nozaki-Hiyama-Kishi reaction of benzaldehyde will take place in presence of this vinyl triflate. Okay, moving to the next question. So this is from the part organomanganese compounds. Okay, so let us look at this reaction step by step. First, what will happen? You have two leaving groups here. Okay, one is iodide and one is chloride, and iodide is being present in the as the vinyl iodide. Okay, so in between these two, if you compare, iodide is much better leaving group. Okay, and in presence of this vinyl group, it is much more enhanced in this case. Okay, so what will happen? This vinyl iodide will undergo metal halogen exchange in presence of butyl lithium. Okay, so the first species that we are going to generate here is chloride here double bond, and here we are going to have lithium. Okay, so if you don't want to show the bond, you can simply write minus here and Li plus here. Then we have manganese iodide. Okay, Mn I2. So this anion is going to attack in such a way that you are going to get an intermediate where you are going to have carbon manganese bond. Okay, now we are introducing our acid chloride, which is this one. So this bond will now break to give you a nucleophilic species of this type, which will get added to the acid chloride, and you will get the chloride knocked out. Okay, so this is how we are going to get 70% yield of this alpha beta unsaturated ketone. Okay, so this is how the organomanganese reagent is going to react. Again, another similar question. This must be very easy for you now. Again, similar reaction will take place. In this position, metal halogen exchange will take place to give you lithiated aryl species. And in the similar way that we have seen in the previous question, this manganese bromide is going to get inserted to the aryl anion. Okay. Now this bond you can visualize as the phenyl group here, and this can attack at the carbonyl compound and the chloride will be knocked out. Okay, so in the same way as we have already seen in the previous question, we are going to get this aryl ketone as the final product. Okay, this is a little higher level of question from the topic organomanganese compound, but if we go to the mechanism step by step, you will find it easier. Okay, let us try to understand the mechanism step by step. So what happens in this particular reaction, manganese is actually acting as an oxidizing agent. Okay, let us look at how it is acting. So we have this alpha beta unsaturated alcohol in the substrate and this sulfone as the second substrate. At first, what will happen? Manganese metal which is used in the reaction is going to oxidize our alpha beta unsaturated alcohol. Okay, and as a result of the oxidation, we are going to get this alpha beta unsaturated aldehyde. Now in the reaction medium, we have our aldehyde and the sulfone left in the reaction medium. Okay, and we are adding a base which is a strong base to the reaction medium. This base is now going to take up proton from this part, okay, because the protons which are present in this carbon are highly acidic, and this acidity is governed by the presence of this CF3SO2 group. Okay, the anion that we are going to generate after deprotonation is highly stabilized because of the presence of this aryl group and this SO2 CF3 group. Okay, so this is why we are going to generate an anion at this position using potassium tertiary butoxide base. Now this anion is going to undergo 1,4 addition to our aldehyde, and you are going to get this particular product. Then in the next step, what will happen? Another molecule of base is acting, and in this case we are going to generate the second anion at this position, which will undergo cyclopropanation due to the presence of this good leaving group. Okay, and you will end up the synthesis of this cyclopropane carbaldehyde. Okay, and at the end, the regeneration of the manganese catalyst will take place, and the manganese manganese hydride that we got in the very first step of the reaction is now going to reduce the aldehydic functionality back to alcohol. Okay, so this is how at first our alcohol is oxidized, and at the end it is again reduced after the cyclopropanation step. So this is an uncommon reactivity of the manganese metal which is acting in this particular reaction. Okay, again let us move to the mechanism of the next question, which is from the organomanganese reagents. Okay, so in this particular reaction, this reaction from I have taken from a research article, and that research article has claimed that the addition of this organotitanium reagent enhances the yield of this reaction. Okay, let us look at how this organotitanium reagent is taking part in governing better yield or better selectivity. Okay, so at first, if you look at your substrate, we have this carbon halogen bond which is alpha to the ester. Okay, so that carbon halogen bond is going to be broken by the organotitanium reagent, and we are going to get a radical of this type. Okay, so the organotitanium reagent is governing the reaction to follow a radical pathway. So after the formation of this radical, this ketone will undergo enolization, and we are going to get our second intermediate of this type. And after the formation of the second intermediate, what will happen? The enolate is going to attack at the aldehyde carbonyl carbon. H. So here we are going to get the attack, and after the workup we are going to get this beta hydroxy ketone as the final product. This beta hydroxy ketone we are going to get as the final product. Okay, now let us move to this interesting question, which is from the topic organo-zinc reagents, and to be precise, it is from the topic Reformatsky reaction. Okay, so if you look at the reaction products, these two reactions are highly enantioselective. Okay, and this enantioselectivity is governed by the addition of these two chiral reagents in the reaction medium. Okay, so Professor Pan sir has also covered enantioselective organometallic reactions in this topic, so you can also go through those examples to better understand the selectivity. Okay, so we are only going to look at the reaction mechanism now, how it is taking place. So if we recall the mechanism of Reformatsky reaction, at first the zinc metal from the dimethyl zinc is going to be inserted between the carbon iodine bond. Okay, and you are going to get a species of this side. Here you are going to have the ester, and here you have Z, Zn, I. Okay, so this is the species we are going to get, in which we have a nucleophilic part of this type and an electrophilic part of this type. Okay, so the nucleophilic part is now going to attack at the aldehyde, which is bromobenzaldehyde in this case, and by workup we are going to get this beta hydroxy ester as our final product. So this is the reaction mechanism that this Reformatsky reaction is going to take place, and the enantioselectivity is coming from this chiral center, which is now newly formed. Okay, And if you look at the second reaction, that is also the same substrate and same product, just in place of the chiral reagent, this reagent 2 is added. And if you look at the stereochemistry of this chiral reagent, it is S chirality. Okay, so you are going to get enantiomerically excess product, which is, you can see that 80% enantiomeric excess you will get at this chiral carbon center. Okay, so this is how this Reformatsky reaction is going to take place. Moving to another reaction from the organozinc part, which is the Simon-Smith cyclopropionation. Okay, so in Simon-Smith cyclopropionation, what happens is this type of a reaction mechanism is involved in case of Simon-Smith. Okay, so this is the transition state which is formed, which is coming from the double bond of our substrate and the CH2 group, which is used in the Simon-Smith cyclopropionation reaction. Because if you look at the reaction condition, we have the CH2I2 and copper zinc metal. Okay, and in presence of these two reagents, we are going to get a zinc organozinc complex of this type, which is CH2ZnI2. Okay, CH2ZnI2, and this CH2 from this organozinc fragment and the double bond from the substrate are going to coordinate to give us a three-membered transition state. Okay, and this three-membered transition state will be followed by the knocking out of Zni2 and insertion of the CH2 to the carbon-carbon double bond. Okay, so here you can see that the products are the cyclopropane and Zni2. Okay, so if we go back to our reaction, here also similar reaction mechanism is going to be followed. Here we have the double bond, and this double bond is going to undergo reaction with CH2ZnI2, which will form in situ in the reaction. Okay, and this will undergo cyclopropionation via a three-membered transition state, and you will get this cyclopropane here. So if you have a confusion regarding the stereochemistry of the cyclopropane, that why the incoming CH2 from the CH2ZnI2 is coming from below the plane. Okay, so what is happening? If you look at the substituents present on this decalin part of your substrate, okay, so you will get to know that in 3D this part will be like a open book. Okay, this part will be like a open book, and these two cyclohexyl rings will form a bent book kind of structure. Okay, if I write it from the side, you might know. So suppose you have OH here and methyl is also in the below the plane. Okay, and these two will be bent like this. In this shape, these two cyclohexyl rings will be bent. So, because of this bent structure, the incoming CH2ZnI2 will face high steric hindrance, okay, from these two cyclohexyl rings. And this is why the below face is more approachable for the CH2ZnI2. And this is why the cyclopropane ring which is newly forming is, you can see, lying in the below face. Okay, this is again another example of the topic Simon-Smith cyclopropanation, and here the similar mechanism is going to be followed where you are going to get cyclopropanation of this carbon-carbon double bond. And in this case, the stereochemistry is going to be governed by this chiral reagents which is used in the reaction. This particular chiral reagent is going to give you this cyclopropanation in the above phase. Again, this is the same reaction where we have the organozinc complex and we have this double bond. The same mechanism will be followed to give us the cyclopropanation in the double bond. So, coming to the last topic of this week's video lectures, which was organomercury reagents. Okay, so organomercury reagents are widely used for synthesis of this type of tertiary alcohols. Okay, and mercuric acetate followed by treatment with sodium borohydride condition is widely used for such synthesis of tertiary alcohols. So if we look at the mechanism, what happens? This is very easy. You must have already studied this reaction in your bachelor level also. So what happens in oxymercuration demercuration? At first, mercuration of the double bond take place in this way that the mercury will be trapped by the double bond in such a way to give you this mercurinium ion. Something similar to the iodination also. When we subject an olefinic double bond for iodination, we get iodinium intermediate at first. So similarly, in this case also we get a cyclic mercurinium ion by knocking out one acetate from the mercury acetate. Now this mercurinium ion is attacked by water, okay? But before the attack of water, you have to decide the stability of carbocation that can be formed from our substrate. For example, see, we have this double bond, okay, which is going to get mercurated at first. So suppose we are forming our mercurinium ion in this way. Okay, and this double bond will not be here. So here you have one acetate. So in the subsequent step, what will happen? This mercurinium ion will open up, and you have two possibility of opening this. Okay, either this or this, but the opening will be governed by the formation of the more stable carbocation. See, if we open the mercurinium ion from this side, we are going to get a carbocation here. okay, which is a tertiary carbocation. Whereas if we open this mercurinium from this side, we are going to get a less stable secondary carbocation. So, as we know that tertiary carbocations are more stable than secondary carbocation, so we will definitely open the mercurinium from this below side, okay. So, the next intermediate organomercury intermediate that we are going to get is this one, okay, OAC, and here Me, and at this position we are going to get carbocation, okay. Now this carbocation is going to be attacked by water molecule, okay. The water will attack at the carbocation and you are going to get a water addition of this type and we will get a oxonium ion. That oxonium ion can undergo deprotonation to give us the alcohol, okay. And at the end, sodium borohydride will cleave the carbon mercury bond to give the desired alcohol, okay. So this is how this oxonium that we are going to get first will undergo deprotonation and this carbon and mercury bond will be cleaved using sodium borohydride. So if we talk about the below question, there also you can expect that, see this side your carbocation will be more stable, right? So in this case also you are going to get a carbocation here and the mercurinium opening from here and this will be attacked by a water molecule and ultimately you are going to get 87% yield of this tertiary alcohol, okay. So thus we have today discussed various questions from the topics organometallic reagents which were covered in this week, okay. Let us quickly go through all the questions that we have discussed today. Okay, I will just reopen the slide because I have written a lot of things on this one. Okay, so we started the question series with this organocuprates, okay, and we talked about how organocuprates prefer to get added in the 1,4 fashion, okay, rather than 1,2 fashion, and that is governed by the HSAB principle. And whenever in the workup step you have a reagent that can be trapped by your enolate, then you will not get an alcohol, but you will get the trapping of the second reagent in this way, okay. So then we talked about the selectivity of organocuprates, okay. See in this first question, as you can see, we have two double bonds. One is having ketone functionality in the alpha position and one is just simply terminal olefin, okay. And in between these two olefins, the organocuprates will always choose the 1,4 addition of an alpha beta unsaturated ketone. And when you have a fused phenyl substituent of this type and uh, alpha beta unsaturated ketone of this type, the phenyl ring will stay undisturbed and the reaction will take place only with this alpha beta double bond. Then we talked about Lipschutz reagent and how this Lipschutz reagent gave better yield and better selectivity when it comes to organocuprates reagents. Okay, and we also talked that the incoming nucleophile is going to attack the epoch site from the less sterically hindered site. Then we talked about this biaryl coupling reaction in presence of organo copper reagents. And this particular reaction is going to generate in situ Lipschutz cuprate, which leads to the biaryl coupling reaction. Then we discussed this Glaser coupling reaction, and we also went through the reaction mechanism, how in presence of base the organocopper reagents undergo the formation of four-membered metalla cycles. Okay, and then we talked about this particular reaction where we observed both homo and hetero coupling of alkynes. Okay, and we discussed how iron and zinc both were taking part in the reaction mechanism. Then we talked about Dodge annulation and its importance in the natural product synthesis, because starting from acyclic molecules, we were going to get cyclic annulated products. Okay, and we also discussed the mechanisms involved in these two reactions. Then we moved to organochromium reagents, and there are a few easy reactions. And we also talked about Nozaki-Hiyama-Kishi reaction mechanism of this particular reaction starting from benzaldehyde. Then we moved to organomanganese reagents, and we saw how at first the vinyl iodides undergo metal halogen exchange in presence of butyl lithium, and then that undergoes reaction with organomanganese complex, and it acts as a nucleophile to get added to electrophilic substrates to give these type of cyclopropane carbaldehydes or cyclopropane ketones. And another similar reaction we discussed in presence of organomanganese reagents. And this reaction was found to be a little exceptional, where we saw that the manganese was acting as a catalyst by at first oxidizing the alcohol, and at the end, to get the desired product, manganese was also reducing the aldehyde which we got initially. Okay, then we discussed this reaction in presence of organotitanium complex, where we got a similar kind of reactivity to get a final product which is beta hydroxy ketone. Then we talked about the mechanism of Reformatsky reaction and how addition of chiral reagents can give us selectively, enantioselectively selectively a particular product. And then we discussed the mechanism of Simon-Smith cyclopropionation, and we also went through all these examples of Simon-Smith reaction. Okay, and lastly we have discussed organomercury complexes, where we have seen the synthesis of tertiary alcohols starting from the olefins. Okay, and the involvement of the more stable carbocation intermediate is crucial in this oxymercuration demercuration reaction. So I hope you have well understood the reactions which we have discussed in today's tutorial. Okay,
Thank you, madam.
thank you so much.